All right, guys, welcome. We are going to get started on our CCNA course. We're going to start with Section 1, and in Section 1, we're going to talk about exploring the functions of networking, right? Obviously, this class is focused on networking concepts. We're going to be talking about a lot of networking technology. The one big change that they made with the CCNA, of course, is that they took all these different CCNAs that they had previously, CCNA Data Center, CCNA Security, CCNA CyberOps, CCNA Wireless, and they combine them into one class, right? The CCNA Administering Cisco Networks. And so in this particular class, we do talk about a lot of different topics, but we still focus on some of the fundamental aspects of networking, right? The OSI model, the Open Systems Interconnect model that talks about the relationship of communication from one layer to the next, from the physical layer to the data link layer to the network layer to the transport, the session, the presentation, and the application layer. We also, of course, talk about managing Cisco devices like routers and switches. But as you can see from the diagram here, a network consists of a lot of other components, right? A lot of different protocols that we're going to see that we talk about throughout the class. Both routed and routing protocols, like routed protocols like TCP/IP applications and routing protocols like OSPF. In the old CCNA, we would talk about things like EIGRP and even BGP, and we would even get into a little bit of RIP routing as well. We don't do that so much in this class, but routing concepts are really, really critical, and we're going to spend quite a bit of time talking about that. Networks are traditionally have always consisted of having endpoint devices like PCs and printers and computers, but we've also had devices that allow us to interconnect those components and to transport the data, right? I told you guys in the introduction about the 10-base-2 and 10-base-5 networks that I worked with in the past, which was our physical layer topology that allowed us to allow devices to communicate. Now pretty much everything is twisted pair Ethernet or wireless, but it's still the same concept. We still have applications and protocols that we have to run across the network. We still have to manage those applications and protocols, and hopefully throughout this course, you guys are going to learn about those specific details. We're going to be doing quite a bit, actually. We're going to be doing Wireshark captures. We're going to be doing bit level and analysis, taking a look at packets and frames, and when we're talking about how a switch operates in the book here, I'm going to be demonstrating some of those concepts, and then I'll be doing some captures and showing you some real in-depth information. So we're going to expand quite a bit beyond what we see normally in the class. We're going to get into quite a bit more. All right. So as it says here, right, a network is a network of computers and components that are located relatively within close proximity, right? At least within a LAN. That's what we talk about, a local area network. These are computers and components that are within a relative close proximity, typically high speed, gigabit or faster, and so on. But back in the day, when I started teaching CCNA many years ago, we always used to teach this thing called the 80-20 rule. You guys ever heard of that? 80-20 rule? 80% of the traffic is switched within the LAN and 20% of the traffic is routed, right? Because routing, number one, was complex. It wasn't very efficient at the time. Everything was classful, so we couldn't do things like subnetting and so on. But what was the other problem with routing? It was expensive, right? Routers were expensive, and they weren't easy. Routed networks were not easy to implement. Now it's more like the 20-80 rule, isn't it? 20% of the traffic is local and 80% of the traffic is routed. And what's changed in networking today that has forced that concept? Virtualization, right? And that's a big part of this class. In fact, we have sections towards the end of the class where we actually talk about network virtualization and why virtualization is so important. We also talk about in this class the concept of software-defined networking, right? And on our YouTube channel, I would definitely recommend this. There are a couple of different courses out there about software-defined architectures. And that's kind of becoming the new norm, right? Network automation, programmability, that kind of thing. it's not that the fundamental concepts of networking are changing. We're not getting rid of OSPF. We're not getting rid of MPLS. We're not getting rid of traditional routing and switching concepts. We're automating the configuration and management of the infrastructure. And that's what software-defined networking is. It's network automation. Driving the configuration policies and the principles of configuration on the network based on high-level thinking, business architectures and stuff like that. And using automated tools to be able to push out those policies and configurations. All right? So when we're talking about networking, they have 3 bullet points here. There are some important skills that you have to build on. Explain the functions, characteristics, and common components of a network. Primarily in this class, routing and switching, right? Yes, there's a wireless component, but basically wireless components are basically bridges, right? They're bridging a radio frequency connection to an Ethernet connection. You'll be able to read a network diagram, including comparing and contrasting logical and physical topologies, right? What is a star topology? What is a bus topology? What is a mesh, a partial mesh, a full mesh, a hybrid architecture, stuff like that we'll talk about. And what is the impact of applications on the network, right? When we think about applications on the network from a network engineering standpoint, what are the 2 primary things that we concern ourselves with? I mean, if you really have a security hat on, it's always 3 things, but typically it's 2 things that we're concerned with. Availability, right? The availability of the applications and resources for users to use. And availability doesn't mean that it just works. It means that it works efficiently and that it works correctly, right? That's a very important concept. So availability is important. How do we maintain or achieve availability in network design? We offer things like redundant components, building in redundant routing points in the network, building in dynamic protocols that can adjust or make changes based on issues or trouble that might occur in the network. We have redundant resources, redundant switches, redundant routers, redundant power supplies, and we run robust routing protocols and robust switching protocols. But the other aspect is going to be security. Security is a big part of that. And we will be talking a little bit about security in this class. We don't necessarily get into firewalls specifically, or IDS or IPS or security architectures. We talk about security protocols. We'll talk about things like port security and, of course, segmenting the network into VLANs and access control lists. We're going to spend quite a bit of time talking about access control lists. Traditional network security architectures. Unfortunately, when they got rid of CCNA security and all these other classes, they had to kind of decide what was going to be important in the new CCNA, because now you're talking about a course that's supposed to be, a mile wide and only about an inch deep. So we don't get into all these topics in a whole lot of detail. But I'll be more than happy to answer any questions that you guys might have. All right, so we'll get into that as we start to go through it. What is a computer network? I don't think we need to spend a whole lot of time on this. I think you guys have a pretty good understanding of what a computer network is. They have a pretty picture here of what an old computer network used to be. But let's talk a little bit about how computer networks have evolved and changed, because that's really important, actually. Back in the day when I started doing computer networking, even this was a little bit before my time, but we didn't have a whole lot of options for transporting data over the network. We only had a few network operating systems that we could use in our applications, things like Novell and Windows for Workgroups, and you still had AppleTalk and some other transport protocols. But from a connectivity standpoint, we didn't have a whole lot of options. You had a 10 meg Ethernet network, or maybe you had 10 base 2 or 10 base 5 architectures. Now we have so many more choices, right? But what's probably one of the biggest changes that we've seen in the realm of connectivity over the past, say, 10 years in an enterprise network? I know you guys know. wireless, right? Hasn't wireless really evolved more than anything else? I mean, has Ethernet really changed, right? The Ethernet that we use today, and we'll see this in Wireshark, Ethernet 2 is the same Ethernet that was developed in the 70s by Xerox. Xerox and Intel and Digital Corporation. They got together, they formed something called the DIX Consortium. DIX stands for Digital, Intel, and Xerox. And they developed a LAN communication protocol called Ethernet 2. If I was to open up Wireshark and start doing a capture, you'd see I'm still running Ethernet 2 today. You guys ever heard of 3Com? 3Com, back in the day? Stands for 3 companies. Guess who the 3 companies were? Digital, Intel, and Xerox. They formed 3Com. They have the Etherlink 3 adapter and twisted pair Ethernet and so on. So obviously, computer networks today have evolved, but one of the questions that I get often when it comes to identifying, your roles or responsibilities as a network engineer is a lot of people will say, well, what's the difference between me being a network administrator and me being a network engineer, right? I always had a little bit of an issue when I got out of college because everybody was calling themselves an engineer, right? I had 2 engineering degrees, and I always took kind of offense to people calling themselves, I don't call myself a doctor because I, know how to put on a Band-Aid. But my thought process changed quite a bit because you start to get into the actual design and not just pasting in configurations or implementing some basic configurations, but actually designing the network is pretty complex, right? I always tell my students it's easy for me to teach you how to implement OSPF or implement EIGRP or implement BGP. It's not as easy to teach you how these things work, how the protocols work, how the algorithms work, how to engineer a solution so that it's as efficient as possible. And computer engineering and network engineering is really what it's all about in that regard. So we'll get into that. As far as the components of a network, Cisco actually uses a model, and you'll see this quite a bit in a lot of their documentation, the enterprise campus model, right? Modular network design is nothing new. It's been around for a long time, and a lot of vendors do promote network design in this modular framework because what they like to do is they like to define functions of the network or roles and responsibilities of the network based on its function within the enterprise. So this is kind of a step away from the more traditional documented modular design model that Cisco publishes in most of their books, but it does give you kind of an idea of how Cisco looks at the overall network architecture. You have remote sites, branch sites, small office or home office sites, and they have their individual network components. You might have an internet-based WAN connection, which is actually becoming more and more common. We'll talk about that in a minute. And then you have your WAN. What's the difference between the WAN and the internet? WAN is usually service provider managed, whereas internet is open, right? It's just public internet. Traditionally, we always stayed away from the internet, right? Number one, because of security concerns with the internet. Number two, because it just wasn't reliable. You couldn't get the speeds or the bandwidths that you needed. There was no quality of service because quality of service has to be kind of managed and guaranteed throughout the entire path, and service providers were not running any kind of quality of service. So, the internet was just kind of there for internet type stuff, personal use type stuff. The problem with the WAN, though, service provider managed WANs, is that we had limited bandwidth typically, but they were also very expensive, right? Some of the traditional WAN technologies that we've seen in the past are ATM, asynchronous transfer mode, and frame relay. Now we're moving into, everybody talks about SD-WAN now, software-defined WAN. But SD-WAN is really just an overlay network. right? The underlay network, what's used for transport hasn't changed. When you go out and you start to research software-defined WANs and whatnot, you really start to realize it's just an overlay management application that we use. We have different types of nodes that perform different functions within the software-defined architecture, but the transport is still the same. And probably one of the most common WAN transports that we see today is MPLS, multi-protocol label switching, all right? And you guys have experience with MPLS? A little bit? Yeah. MPLS is kind of one of those strange protocols that operates kind of at layer 2 and layer 3. There's a layer 2 and layer 3 component. There's a couple of different ways that you can implement MPLS, but it is a service provider managed service. Whether it's operating as a layer 2 pseudo wire or as a layer 3 VPN, it's still service provider managed. The benefit to that, though, is that you do get guaranteed service levels. The service provider is going to provide you with guaranteed service levels, and you can implement things like quality of service and so on. When we use the internet as our WAN transport, our wide area network transport, typically we need to concern ourselves with, again, reliability, redundancy, and security, right? If you take any kind of security class, you're going to learn about the 3 cornerstones of security, right? Confidentiality, integrity, and availability. That's that CIA triad. If you did Security Plus, you learned all about that. Or even in CCNA security, they talk about that. Confidentiality is achieved through what? Encryption. I mean, data in motion, typically confidentiality is achieved with encryption. Well, do we concern ourselves with encryption over a service provider managed network? Not typically. Usually those are privatized circuit paths anyway, whether they're switched virtual circuits or permanent virtual circuits. But on the internet, we don't have that option, so we have to add confidentiality. Integrity, making sure that the data isn't modified, either intentionally or unintentionally, as it moves from point A to point B. And then, of course, availability, making sure that we always have connectivity. And availability is achieved through redundant connections, multi-homed, multi-service provider connections, and so on. So on the internet, if we're running an internet-based WAN, we would implement things like Get VPN or Flex VPN or even DMVPN, Dynamic Multipoint VPN technologies. Inside the enterprise campus, you might have a LAN access module, you might have a core module, and even in between that, you might have something called the distribution module. Traditionally, that's what Cisco has always promoted, is a 3-layer hierarchy, core, distribution, and access, and we'll certainly see some of that later on. You might have a data center component. You might have a remote access or VPN component that's attached to the WAN. You might have I know it shows here the LAN core connected to the WAN, but you might even break up those functions. You might say, okay, let's have an enterprise edge module, and that enterprise edge module is going to connect our service provider managed VPN as well as our our self-managed VPN. So this concept of modular design allows us to compartmentalize the function of the network. And then we will decide what protocols, what types of applications we're going to run within those blocks, right? So for example, the LAN core. You'll see there we've got redundant core switches, we've got maybe redundant WAN routers or firewalls that connect to the internet. Notice a lot of redundancy. That addresses the availability concept that we talk about in networking. But the primary purpose of the core is to interconnect the other modules, but it's also for high-speed packet delivery, processing data as quickly as possible. We'll get into it a little bit more later on, but it definitely is important to understand these individual components because they have to be designed to work together, and that means that we're going to have different protocols and different communication architectures that we're going to have to support to be able to do that, right? And we'll get into that throughout the course as we start to break down each module, all right? So when it comes to the types of devices, this is also something that's changed quite a bit over the years, right? Traditionally, in most networks, you really had only a handful of devices you ever had to worry about connecting your network, connecting to the network. You had your PCs, your desktops, whatever they might be, Mac or PC. You had your infrastructure components, your routers and switches, which have been around since the 80s and 90s. And then you had maybe your peripheral devices, maybe some printers. Probably didn't have too many cameras, too many security cameras. You didn't have IP telephony or telephones and stuff like that. Nowadays, everything is connected to the network. Everything is. I mean, I literally have, and I'm not joking, I just got these. I have rat traps that will send me a message when a rat gets fried in the rat trap. It's connected to my wireless network. And it says, you caught a rat, and then I have to go clean the trap. Everything is connected to the network these days, right? This is called IoT, the Internet of Things. That's a term that's been around for a few years. That's because everything is attached to the network. Now, you guys working in the defense space or the contracting space probably don't see it as much as you might see in the public sector, but you know, we certainly do have more devices that attach to the network these days, even in a standard enterprise environment. No, you're not going to have the rat traps and stuff like that, but you're going to have security cameras. You're going to have phones that are telephony endpoints, or what we call TUIs, telephony user endpoints, or interfaces, I should say. You're going to have security components like firewalls, IPSs, IDSs, you know, data center components, computers, and stuff like that. When it comes to network design, do we have to take into account other things now when we're designing the network? Absolutely. Because this traffic, all this traffic has unique requirements. Each type of traffic has a different type of requirement. For example, you might have in your data center some storage solution, right? Well, what do most storage solutions require that other computers don't require in the network? They require the ability to process data in very large segments, jumbo frames, right? So you might have to set up a network that supports these very large frames that exceed our standard MTU sizes. Certainly with cameras, with IP phones and whatnot, we have to concern ourselves with things like quality of service, because some of those applications are time sensitive and delay sensitive and drop sensitive. So quality of service becomes something that gets discussed quite often. And then, of course, we have intelligent control plane devices, like a wireless LAN controller. A wireless LAN controller is kind of a central control point to control of our wireless architecture. But it's not just provisioning and deploying access points. That wireless LAN controller is providing centralized security functions. It's providing the ability to manage the radio frequency spectrum. So these access points are now intelligent monitors of the radio frequency spectrum, and they can report real-time statistics back to that controller, and they can change their power levels, they can change their channels, they can change their frequencies, they can dynamically adapt to what's happening in the environment, right? From a security standpoint, things change a lot as well, right? We have CYOD and BYOD models now, and you don't see it too much in the public sector, but in the private sector you see it quite a bit, right? The CYOD or BYOD. What's the difference between CYOD and BYOD? What is BYOD? Bring your own device, right? A lot of times now companies will say, you know what, we're not going to provide you a laptop, but we will help you set up all the necessary applications on your own personal laptop. That obviously introduces a whole bunch of different security concerns, as well as management concerns. CYOD is a similar concept, but rather than just allow anybody to bring whatever device they want, they have to choose from a list of devices. So we may say, well, we're going to support smart tablets, but we're only going to let you choose between these 3 models or these 3 types of tablets. That's all we're going to support. So a CYOD or a BYOD model is pretty popular, but that introduces a whole nother concept of management. I mean, we're talking about things being concerned about data leakage, right? Losing sensitive or proprietary information. We're talking about the same security principles that you might apply to your traditional data environment. Bob might not apply when he takes his laptop to Jamaica when he's on vacation, right? And leaves it at the beach or something like that. So now we have all these other concerns about data integrity and data protection, data mobility, the ability for people to work and create. And now even with what we're dealing with today, now it's even more, right? Because now people are telecommuting, working from home, and so on. All right, so you'll see, we don't get into it in this class, and they don't actually have it listed on here, but there's a central component to Cisco's kind of BYOD/CYOD model that's called ICE. Have you guys heard of that? Identity Services Engine, Cisco ICE. Cisco ICE is basically Cisco's security platform, but for both wired and wireless architectures. But ICE is a nice platform because it does device profiling. It'll allow you to identify what types of devices are attaching to your network. It does device posture assessments. So you can put an agent, a NAC agent, or what we call a network access control agent on that device, and it will go out and it'll scan that device to identify if that device is suitable for connectivity. So do you have the right software? Do you have the right antivirus? If you're running antivirus, do you have the latest antivirus definition file? Those kinds of things.
Have you heard of Forescout before?
Sorry? Yeah. Mm-hmm. Yeah, same concept. It's what we call an 802.1x architecture, extensible authentication architecture. Cisco has their version, of course, other vendors. Norton Security has one as well. There's several different vendors that have these device security applications, but security becomes less static and more dynamic, right? We're able to identify what types of endpoints are connecting. We're able to profile and posture those endpoints to be able to make sure that they meet the criteria that were required for them to be able to attach. And then we can even do things like remediation. We can say, okay, you need to do X, Y, and Z. Once you do X, Y, and Z, come back and we'll do a change of authorization and we'll let you connect. But until you do these things, we're just going to give you guest access, or we're going to put you into this remediation VLAN where you can get access to the software you need, but that's it. You're not going to get access to corporate resources. So it makes our jobs a lot more challenging because now, as a network engineer, we're supporting all of these functions. We need to make sure that the routing and switching supports the voice over IP environment. We need to make sure it supports the Cisco TrustSec and the 802.1x security environment. But guess what sits at the foundation for all of those things, right? All these different pillars of communication, network foundation. You don't get away from routing and switching. It's still there. So switching concepts haven't changed over the last 20 years. Routing concepts have barely changed. I think the last major routing change that we saw was in the mid-90s, right, when OSPF and EIGRP came out, and BGP. We haven't really seen any kind of changes outside of maybe how we implement it, but as far as the underlying principle of communication, it's the same. So we'll get into that, but obviously we have lots of different, we got our endpoints. Endpoints even have their own kind of unique requirements. We've got our intermediary devices, but don't forget the one thing that's also important as well, right? The one thing that's important in all this as well is the physical layer. Physical layer. I mean, think about, I mentioned this real briefly a little bit ago, but wireless has changed so dramatically. And even the wireless stuff that we saw 2 years ago is being, WPA3 is coming out. We've got new wireless standards that are operating in the 10, 20 gig range. So it's changing a lot. And the physical infrastructure is now, we're running into a situation where the physical architecture is not supporting the technology. There's a video on our YouTube channel about this multi-gig Ethernet technology that Cisco is developing. Because if you think about it, even 802.11ac, right? Wave 2 or Wave 1 or Wave 2, you're dealing with speeds of 4 or 5 or 6 gigs of throughput on an access point. But you don't have uplinks to the APs that support that speed, right? You don't have 2.5 gig uplinks or 5 gig uplinks because they're gigabit ports, right? And a lot of people haven't implemented 10 gig Ethernet to their endpoints. So this multi-gig technology allows us to take a standard 1 gig Ethernet port and push 2.5 to 4 gigs through that port without having to change the underlying physical layer or the infrastructure. It's kind of an interesting concept. They're multi-gigabit Ethernet. But all right, so we got endpoints, we got routers, we got switches. Of course, we'll talk about that. APs, wireless LAN controller, next generation firewalls. That kind of goes along with what we were talking about with the next generation security. In Cisco speak, anything that basically is an X next to it is considered next generation. A 3850X or a 5505X or 5510X or whatever. But a next generation firewall is really just a firewall that's application aware. It has the ability to not only do traditional firewall things like blocking or allowing traffic based on policy, but it can actually dynamically assess applications. It can look at application payload information and make firewall decisions based on actual payload information and application characteristics. Kind of goes along the lines with the next generation IPSs and IDSs as well. Speaking of that, by the way, in the concept of IDSs and IPSs, what is the fundamental difference between an IDS and an IPS? One stands for intrusion detection system, one stands for intrusion prevention system. But what are the fundamental differences? One is offered in inline mode, and the other one is offered in what we call tap mode or out of band mode, right? IDSs typically will sit on the side of the network, and we will maybe do some span port or something to that device, like a network tap or a logical network tap, and we'll send information to that device for analysis, and we can report on that information. So an IDS can trigger events, SNMP traps or syslog events, or it can trigger some sort of notification if it identifies a potential threat, but it can't take action directly, right? It's limited in taking action directly because it doesn't sit in line with the traffic flow. That's not to say that it can't tell a router or tell a firewall or tell some other device that is in line to do something. It can. It just can't take action directly. That's a detection system. In the context of IPS, intrusion prevention, that typically sits in line with the traffic flow, inline mode, and it can take action against the flow. It can do a TCP reset. It can block the connection. It can block the host itself. There's lots of different actions that can take. When it comes to intrusion detection and prevention, many, many different options with those different devices as well. We can do heuristic analysis like anomaly-based detectors where we have a baseline capture of what normal traffic looks like. And then if anything happens outside of that normality, then we identify that as a threat. We could have signature-based intrusion systems. A signature-based system basically will look at characteristics of packet flows and whatnot, and then look for specific signatures of events. These would be predefined signatures of events. We could do policy-based engines as well, where we're basically taking action based on a policy that you define as an administrator and so on. So there's all types of intrusion types of protection that we can have. We try to employ systems that have are effective against zero-day attacks, right? What is a zero-day attack? Or some people call it a day zero. Yeah, go ahead. Right. It is the type of attack vector that hasn't been identified or defined previously, right? So it might have they might have a hybrid or a variation of a previously defined attack, but they change one aspect of it so that it looks new, or that we don't trigger, right, on a particular event because it doesn't have the same characteristics that we were looking for, and so on. So that's one of the things that we try to protect against. So management services, of course, we always worry about something called network telemetry. And there are many aspects to network telemetry, but one of the key aspects to network telemetry is being able to capture information about particular events that are important to us, right? And we do that through various protocols, but two of the primary protocols that allow us to capture events are syslog and SNMP, the Simple Network Management Protocol. Of course, these events are time-stamped and logged, so we want to make sure that our network time is also a consideration, which we'll talk about a little bit later on. So here's a pretty graphic that kind of talks about all the things that we talked about. But again, that's really what this course is all about. We don't focus a whole lot of time on the endpoints themselves, like what is a printer and what is a scanner and what is an IP phone. But we will talk about the impact of implementing these, this kind of ecosystem of endpoint devices on the network. Because like I said, each one of these has different requirements for connectivity. They have different concerns from a security perspective. They might have different protocol requirements. They might have different connectivity requirements, and so on, all right? Intermediary devices, mainly switches and routers, right? They classify an access point and a wireless LAN controller as an intermediary device. I guess to a certain extent that's true, because an access point is just basically a bridge. It's just taking some wireless connection and transmitting over or converting it into some LAN-based connection. And then we have the media. We are going to spend some time talking about media. We're going to talk about twisted pair Ethernet. We're going to talk about different cabling types. We'll talk about fiber. We'll talk about copper. We'll talk a little bit about wireless. That's mostly part of the self-study section. And then the services that we run on the network. All right? There are services that are required for the network to function, like spanning tree, like routing protocols, like basic LAN switching protocols. And then there are services that are required for the devices to function. Application services, DNS, DHCP, applications like FTP or Telnet or SSH, protocols that we just kind of use on a regular basis. We spend a little bit less time in this class talking about the application protocols for endpoints and more about the application protocols for the infrastructure to work. All right? All right. Now, what are the characteristics of the network? We can describe the qualities and the features of a network based on specific characteristics. Number one, the topology, right? Now, in the past, topology was a big concern because we had a couple of different options for how we implemented the topology. And it would either be a bus or it would be a star topology. Let me actually bring something up and show you what I mean about that. What I mean by that is that in the old days, when networking was just coming out, we had these different options for physical architecture. We had something called a 10-base-2 network, and literally you would create the network by basically connecting the computers together with this cable. If I can get over there we go. With this cable, which was constructed of coax, and you would literally have these T connectors, and they would just plug right into the back of the computer, and you were creating this logical bus. And when somebody wanted to, we're still running Ethernet over this network, by the way. It wasn't some crazy proprietary protocol. It was still Ethernet. But if these computers wanted to communicate, they had to compete with each other to communicate. If this PC on the bottom left wanted to send data, nobody else could communicate because that data was being essentially flooded or duplicated to everybody in the network. All right? That was what we called a 10-base-2 network, and literally you were creating this bus topology. This is what it looks like visually. It's how they typically draw it, right? This diagram here. And there was another network that was kind of like that as well. It was 10-base-5. By the way, 10 was the speed, 10 megabits per second. Base was the modulation technique that we used, baseband transmission. And then 5 was the actual length of the segment that you could have, 500 meters. And 10-base-2 was 200 meters. And 10-base-5 network was ThickNet. It was called ThickNet for a reason, because you had these really, really thick cables that you used to connect the computers to the actual backbone. I mean, we're talking Flintstones era networking, basically. You literally, if you wanted to connect to the network, you literally had a backbone cable that looked like this big thick cable right here. And if you wanted to connect to the network, you would put something on there called a vampire tap, which would actually have just a metal pin that would pierce the copper core. And that's literally how you would get connected to the network. It's pretty crazy the way it used to be. And that's what the tap looked like there. Here's the diagram of one right here. You can kind of see it. But, you know, obviously we went from, and that was still considered a bus topology. And then we went to twisted pair Ethernet. So we went to something called a star topology, where you had, in essence, the switch was the center of the network, if you will, and the PCs would connect to that switch. Now, that's basically what a hub looks like as well, but again, a switch and a hub are completely different types of devices. Switches operate at layer 2 of the OSI model. They make intelligent forwarding and flooding decisions, whereas hubs operate at layer 1 of the OSI model, and they flood everything. So even though physically it might look the same, logically they're completely different concepts. A hub is a bus topology, and a switch is a star topology. But this, for example, this diagram that they have here, this would not be considered a star topology, even though it looks like a star topology, because that's a hub in between. Anything that goes into one interface on a hub gets flooded out of every other interface on the hub, which makes it a bus, not a star topology. So don't get confused with that. Just because it looks like a star doesn't mean it is a star. The star topology is really where you have a switch in between that can control how data is forwarded and flooded. We'll get into that later on as we start to talk more and more about the different layers and the different technologies. Now, you also have, with regard to topologies, you have full mesh, partial mesh, hub and spoke. Let me see if there's a diagram I can pull up. Partial mesh, hub and spoke, and hopefully we'll find one here. Yeah, here's a good one right here. All right. Oops, view image. So typically with a hub and spoke, you have a device in the center of the network. And again, this can be applied to a LAN, or this could be applied to a WAN. And these circles could represent actual physical network locations, right? So the center dot might represent my HQ location, and these dots might represent my branch locations, right? This is a ring topology, by the way. That's typically with FDDI or token ring, we would see something like that. But what is the downside to this middle one here, this hub and spoke design? There's no redundancy, right? And also there's no efficient data flow. If one spoke wants to talk to another spoke, they have to go through the hub. They can't just talk to each other directly. And if the hub fails, then the whole network fails, right? You get a full mesh, and in the case of a full mesh, every site is connected to every other site. So that addresses the concept of redundancy. It also addresses the concern for efficient communication. But what's the downside to this design? Price, cost, right? Especially if you're talking about this from a WAN perspective, interconnecting actual physical locations. So then you start to see, I don't know what this one's supposed to be on the right here. That's nothing? Yeah, this is no network, yeah. Yeah, that's definitely the cheapest way. So you get to what we call a partial mesh. A partial mesh is where maybe some of the more critical sites are redundantly connected and some of the less critical sites are not connected and so on. But again, the physical topology does not necessarily define the logical topology. We talk about this a lot when we talk about things like spanning tree. A spanning tree design is a logical topology versus the physical topology. So you might have, for example, let me draw a picture for you guys. A topology that looks something like this, where you have your distribution layer switches, and they're connected together with maybe an ether channel, and then you've got your access layer switches, which are redundantly connected to the distribution layer, right? That's a pretty typical design for redundancy and so on, but it doesn't work very well at layer 2 because it creates loops in the network. So we implement our spanning tree design, and the spanning tree design says, okay, this link is going to be active for the red VLAN, that link's going to be active for the red VLAN, and then this link is going to be active for the green VLAN, and that link's going to be active for the green VLAN. So logically, we've gotten rid of the loops in the topology. We still have the physical redundancy because spanning tree can adapt and change if a link fails. But the logical design looks different than the physical design. And that's something to consider when we talk about things like first hop redundancy protocols like HSRP and VRRP, or even spanning tree and so on. So that's the first kind of bullet point they had here. The next bullet point they had listed here was bit rate and bandwidth, right? Now, you guys are going to learn this as we go through the class. There's a difference between theoretical bandwidth and practical throughput, right? Interfaces themselves have theoretical bandwidth values. A 10 meg interface is theoretically 10 megs. A gig interface is theoretically a gig. Actual practical throughput is going to be based on lots of different factors. How many people are trying to use that path? Is the path efficient? Is there a physical layer problem that might be reducing the amount of bandwidth or throughput that we have, and so on. So they say here, bit rate is a measure of the data rate in bits per second of a given link in the network. Kilobits per second, megabits per second, gigabits per second, and so on. The fundamental unit of bit rate is a bit per second, and then we just do multiples of that. But again, it's important to distinguish the difference between a theoretical value and a practical value. When we're dealing with things like routing protocols, specifically we're dealing with things like metrics, which are how routing protocols choose paths. We always reference bandwidth in terms of theoretical value, not practical throughput, because practical throughput's always changing. And if practical throughput's always changing, that means that we would never converge because the metrics would constantly be changing for networks and so on. If I go to an interface and I change the bandwidth of an interface, for example, by using the bandwidth command, I'm not changing the actual throughput of that interface. I'm changing the theoretical representation of the bandwidth of that interface. So I'm changing how QoS is going to analyze that interface. I'm changing how routing protocols are going to analyze that interface. So that's a pretty important distinction. I suppose the only other thing to say about this particular piece right here is make sure you understand the difference between bytes and bits. I know that's a fundamental concept. 8 bits in a byte, unless you started computing in the 70s, then it mattered if you had parity or no parity. But now it's 8 bits in a byte. If you see a big B, that is a byte, a little b is a bit. So just pay attention to that. You might even see that on the test. They might be referencing something in bytes or bits. If it's in bytes, it's more than the bits, all right? Of course, another thing to think about is availability and reliability. Aren't those kind of related to each other? Availability and reliability? But what is the distinction? What is really the fundamental difference between availability and reliability? Just because something is available doesn't mean it's usable. Just because I can ping a server doesn't mean that the server is going to respond to an application, right? Because maybe ping works at layer 3, right? So an ICMP echo request is a relatively benign packet, but the application might have other requirements. It might have more bandwidth requirements. It might have specific response time requirements. Maybe it's a UDP flow that is highly susceptible to packet loss or jitter or delay. So just because something is available doesn't mean that it's actually usable. So when we talk about things like availability, yes, we need to have the resources available, but they also have to be usable. Now, reliability means also, how often are those resources, do they become unavailable? We don't get into it too much in this class. In my CISSP class and my other information assurance classes that I teach, we talk about things like recovery point objectives and recovery time objectives and mean time between failure and mean time to recovery and stuff like that. So we could certainly get into that when we talk about reliability, but that's basically what they're referencing in this particular case. And they mentioned specifically MTBF, right? MTBF is what? Mean time between failure, right? Typically that's something we would usually associate to a physical resource, like hard drives in a computer or power supplies and stuff like that. We don't really apply that to maybe a router or a router as a whole, or certainly not an application or software. But there are several terms that are used to describe a reliability in network. Mean time to recovery, MTTR, mean time between failure. Like I said, recovery time objective versus recovery point objective. RPO versus RTO. What's the difference between those two? What is recovery time objective versus recovery point objective? Yes?
Recovery time is how fast you need it back up, and recovery point is how far back you need it.
Right. So he said recovery time is how quickly you need it back in operational. What is that typically based on? Criticality of the business, the infrastructure, right? Basically operations. If we do not recover within 24 hours, our business is severely impacted to the point where we might not even exist anymore, right? Recovery point objective tends to be a term that's more used with regard to data than it is to functionality of a business, right? So we want to make sure that we can recover data up to 2 weeks ago or a month ago, and that has to do more with like backups and making sure that data is being stored correctly and so on. That is kind of outside of the scope of the CCNA, but they're good things to know. Good things to know. All right. So they do go through a little bit of an example here. For instance, let's consider a networking device that reboots every hour, and it takes about 5 minutes, after which the device starts working as expected. This diagram shows the calculations of availability and reliability. The availability percentage for the period of 1 day can be calculated as follows. So we have our device information. It reboots every hour, and the reboot duration time is 5 minutes. So we're talking about a 60-minute reboot every 60 minutes. So the reliability mean time between failure is the time in service versus the number of failures. And we have to consider, again, also how much time it takes to reboot. If it reboots every hour and it takes 30 minutes to reboot, then you only have about 50% uptime, right? That's a pretty easy calculation to make. So they go through the example. You're not going to have to do anything like this on an exam, on the CCNA exam, but they calculated about a 91.67% uptime. In most modern networking terms, that's not a very reliable system, right? We're talking about typically trying to engineer what, 5 nines of reliability, 99.999% of the time. But how do we achieve that, by the way? How do we achieve that? We achieve that by getting a better system than one that reboots every hour, of course, but we achieve it by mostly building in redundancies. And we build in redundancies not only physically, but we build redundancies through application. You know, so we put in robust routing protocols that are fast to converge, that don't take a lot of time to converge. We put in redundant, certainly redundant physical hardware, but also redundant redundancy features like first hop redundancy protocols and so on. And we'll get into all that a little bit later on. I would say another important concept in networking today is scalability, because that's one of the things that traditionally was not designed into most networks. You had a certain number of physical ports in your infrastructure. You had a certain number of routers and switches that supported X number of devices, and adding additional devices would put an extreme load on the network. The physical paths didn't support the amount of throughput they had to support, and so on. Nowadays, scalability is a lot easier to design into a network. But here's the thing about scalability. And we're actually going to learn this. Unfortunately, they took out EIGRP, but we still have OSPF to deal with. You can implement OSPF. OSPF, Open Shortest Path First, it's a routing protocol that we use inside of our network. You can implement OSPF in a flat, simple architecture. Everybody goes into the same area. We might have 20 or 30 different prefixes or destinations in the network, but we decide to implement OSPF in a flat architecture. But as the network grows, as we add more clients, as we add higher bandwidth applications, as we add more destinations in the network, scalability becomes a factor. So we have to change the implementation of the protocol, not necessarily the physical hardware or even the paths, but change the implementation of the protocol to add scalability. We'll talk about this later on. We do a multi-area spine and leaf design. Area 0, non-area zeros. We design our physical paths and our redundancy based on that. And then we add our scalability by adding things like route summarization, special area types, all kinds of things that we use to kind of enhance the design. So scalability is not just about physical hardware. That's really the point I'm trying to make. It's about how you implement the design as well. And that's really what I like to focus a lot of attention on, especially in some of the more advanced classes where we get into that a lot more. Of course, security is always a concern. We talked about security quite a bit, right? What about, we've already hit the security piece. Quality of service, we talked about that a little bit as well. That's part of the self-study section here, but if I have a chance, I'll spend probably about an hour talking about QoS, because quality of service, in fact, let me kind of do that right now as part of this discussion. We talk about quality of service. By definition, really, what is quality of service? Prioritizing certain applications at the detriment of other applications, basically, right? But quality of service is not just one thing, right? In fact, there's several different aspects to quality of service. We have classification and marking, right? That's kind of like the first and second step of QoS. We need to be able to identify the traffic. How can I apply different policies to traffic if I haven't classified the traffic into a specific group? And how do I classify traffic? I might use something like NBAR, network-based application recognition. I might use ACLs or other mechanisms, whatever those might be. The two I listed there first are probably the most common. Network-based application recognition, ACLs. Other mechanisms might include things like NetFlow or other type of telemetry applications. What about marking? We will actually talk about marking quite a bit later on when we get into packet formats. But what about marking? Marking is the process of actually stamping the data with some value. There's actually a field in the IPv6 and IPv4 header for marking. It's called the DSCP field, or the toss byte, if you old school, right? So the benefit of marking data would be to say, okay, this packet is XYZ, so at each point along the network, I can make a decision on what to do with that packet based on its marking, right? I mean, you've probably heard of DSCP EF or expedited forwarding or AF or shared forwarding and so on. If not, we'll get into it a little bit later on. So that's like one part of quality of service. Another part, which is what most people think of when they think of quality of service, is congestion management, right? Management, there we go. Is that right? Yeah. This is my queuing or queuing systems. And we have all kinds. We have priority queuing, we have class-based weighted fair queuing, we have custom queuing, we have low latency queuing, which is really just a combination of priority queuing and class-based weighted fair queuing. We have, gosh, there's a whole bunch. FIFO, which is first in, first out, really not any kind of queuing. And I'll just put et cetera here, you get the idea. A queuing system is a way for us to manage the flow of information. Typically, it's going to be on an egress interface, right? So we don't queue packets coming in, we queue packets going out, but we have one physical interface that this data can flow through, and we have to identify who's going to be able to hit that interface first based on a queuing system. And when we talk about congestion management, that's what most people think of when they think of QoS is, I'm going to put this packet ahead of this packet, or I'm going to put this packet ahead of this packet. That is what congestion management is. There's a whole bunch of other stuff to congestion management than just queuing. You have a queue scheduler, so it's the algorithm that's used to process data through the queuing system. You have a way to manage the queuing system. There's hold queue output limits that you have to deal with and congestive discard thresholds and all that. That's probably stuff that you'll see in the QoS section later on. We also have congestion avoidance. And by the way, some of the stuff is on the exam, so it's kind of good that we're talking about this a little bit. Congestion avoidance, there's really only two types of congestion avoidance mechanisms, RED and WRED, which stands for random early detection and weighted RED. And basically the concept of congestion avoidance is I'm monitoring my queuing system, I'm monitoring my traffic flows, and I start to recognize that congestion is occurring. So rather than waiting until the point where I have to basically police or shape all the traffic, I'm going to start dropping data from less important flows to reduce the overall congestion in the queuing system. So it's kind of like a way for us to drop data from less important flows before the more important flows are affected. And random early detection is the way we do that. What else do we have? We have these things called link efficiency mechanisms. Obviously, this is a lot more detail than what the book is going through, but because the QoS piece is part of the self-study, I thought I'd hit this up a little bit. Things like compression, data compression. It could be full data compression. It could be header compression. Some of the common header compression techniques are like RTP header compression or TCP header compression. But the idea, obviously, with compression is that we are trying to shrink the amount of data. What's the downside of a compression technique, though? There's always a trade-off, by the way, with all these mechanisms, but what's the primary downside of doing compression?
Data loss during the rebuild.
Potential data loss, yes, absolutely, if the compression techniques are not very granular. But what about just computation, right? Compressing data and decompressing data takes CPU cycles and it takes time. So compression is not something we typically do, but there's this threshold of a trade-off where running compression actually makes it worse than better. So it's not always, these are not always going to be techniques that you would always apply. Obviously, compression is going to be something that's going to be used more on very, very slow speed links. LFI is another link efficiency mechanism. It's fragmentation and interleave, link fragmentation and interleave. All right. Now, the idea with this is that you've got flows of information that are passing through an interface, and that interface is only has a specific amount of bandwidth, right? And so we've got this router here, and we got this interface. We need to send data through that interface. Well, that interface only has a certain amount of bandwidth. A lot of applications are not necessarily bandwidth, they don't have heavy bandwidth requirements, but they have very stringent time requirements. Like a voice over IP packet, a real-time voice over IP packet, you can't have more than 30 or 40 milliseconds between each packet. That's where we start to get data loss. Well, not data loss, but poor quality because there's too many, the gaps are too large. If I'm talking to him on the phone, I can't delay that conversation. How can I have a normal conversation with somebody if the data that is being sent to him is delayed by half a second, right? It'd be like talking on a satellite phone. You see that all the time, right? On the news, they talk to somebody and then they're just like staring at the screen, and then all of a sudden, 2 seconds later, they start talking. That's because satellite communication is about a 600 millisecond delay. And in real voice, real-time voice, you only have 150 milliseconds that you can really deal with. But anyway, so we've got like these different flows of information. We got the green flow and the blue flow and the purple flow. And each of these different flows have different bandwidth requirements. Maybe this is a high bandwidth flow. And the datagrams are 1,500 bytes, right? And then the green data flow is maybe my voice over IP, and there's only 160 bytes, uncompressed G711 audio. Obviously, the purple flow is going to require more of that bandwidth than the green flow. So, and by the way, once I start transmitting the purple, I can't just stop in the middle. I have to transmit the whole 1,500 bytes, and then I can transmit my green packet, right? The problem is that green packet's waiting for that purple packet to go, and then the time gets too large, and then we start to get degraded quality in the audio signal and all that. So what is link fragmentation and interleave? You take this purple flow and you fragment it. Literally, you divide it up into small pieces, and then you interleave the other pieces in between. So instead of sending the whole 1,500 bytes, you send maybe 40 bytes and then send the green one, then send another 40 bytes and another green one, and you get the idea. This is a function at the more of a physical layer function than a network layer function like fragmentation at the network layer. There are two other things to mention with QoS. There's a lot more to mention with QoS, but the last thing that I mentioned is traffic shaping. Shaping and policing. Now we classify these a little bit differently than congestion management. They could be considered congestion management techniques. They could actually be considered congestion avoidance techniques as well. But shaping and policing are always kind of listed separately because First of all, Cisco loves to test about these two concepts. Secondly, they within a QoS policy, oftentimes we define shaping and policing policies. So typically we will identify two variables within traffic flows, something called the CIR, committed information rate, and a PIR. And a PIR is a peak information rate. And the idea here is we're saying, okay, as an application, we are going to guarantee you this amount of bandwidth. And sometimes we'll let you exceed that, depending on how it's set up, and that will be your peak information rate. Policing and shaping is what do we do if we exceed these values, right? And it's very simple. Shaping delays data, policing drops data. So if we're doing traffic policing and you exceed your committed rate, you potentially, depending on the policy, your traffic will be dropped. If we're shaping, your traffic will be delayed. So that's really the significant difference between policing and shaping. And this is by the all defined within the QoS policy itself. All right? So that's your little crash course, if you will, on QoS. Obviously, the QoS section in your books there, in the self-study piece, that's going to be much more detailed, but this should give you a little bit of an idea. When they talk about QoS, I mean, literally they had one sentence, QoS, right? Well, two, actually. QoS includes tools, mechanisms, and architectures which allow you to control how and when network resources are used by applications. QoS is especially important for prioritizing traffic when the network is congested. Yes, and how do we do that? We use all those tools that I just described, okay? Now, fundamentally, there's two different types of QoS in networks. There's DiffServ, differentiated services, and there's IntServ, integrated services. Most of the case, it's going to be DiffServ, but again, if we have some time, we'll get into that a little bit later on as well. Cost, I always call that layer 8 of the OSI model, right? 7 layers, physical data link, network, transport, presentation, session, application. And then layer 8, budget, layer 9, politics, right? Because as a network engineer, you have to deal with those things all the time. But obviously, cost does drive a lot of decisions. Would it be ideal to have a completely redundant architecture with redundant routers and redundant switches and redundant circuit paths? Of course, but there's a cost associated to that. And oftentimes, cost limits our ability to add those features. And of course, virtualization. Everything is virtualized now. Routers are virtualized, firewalls are virtualized, computers are virtualized, but the nice thing about that is we still have the same tools. We still have the same applications. We still have the same resources available. All right? Oh, they do have it here. Physical versus logical. We talked about this a little bit. The bus topology, the ring topology. You're not going to see ring topology too much these days, right? I mean, there were basically two protocols that provided a ring architecture. Token ring, which was IBM's attempt at a LAN, right? They kind of lost out to Ethernet. And FDDI, the Fiber Data Distributed Interface, which was basically token ring over fiber with counter-rotating rings. Today, it's mostly star topology. When we talk about this later on, we talk about topologies. I tend to focus on logical versus physical, more from the perspective of modern application, like spanning tree, like first hop redundancy protocols like HSRP. If my default gateway is X, that means my traffic is flowing in a specific direction, but that is a physical path, but logically it could be something else if another router takes over that virtual IP or whatever. So we don't have to spend too much time on this. So I think we kind of already hit most of this here. All right. It is important to understand, though, that data flow, and this diagram actually is a good representation of that. you have to be aware of how data is going to flow through your network. Because when it comes to troubleshooting 101 is, what kind of devices are involved in processing the information. In this case, we have what appears to be possibly multiple VLANs with router on a stick. That would be really the only reason that host A would go to the router to talk to the server, is if those devices are in different VLANs. And the router is routing between those VLANs. So even though the physical path looks like it might be directly connected, right? We see that here. The physical path looks like it might be directly connected. Logically, because of how the network is configured, that data is taking a different path. You have to be aware of what that logical path is. When we do our implementations for our clients, not as much today because we kind of design it out, but in the past, we would have to build a physical architecture. We'd say, okay, this is what your physical cabling looks like, this is what your physical architecture looks like, but this is what your VLANs look like, this is the root of this VLAN for this spanning tree instance, this is the root of this VLAN for this. So we would tell them logically what their network would look like as well. So if they're trying to troubleshoot a path and so on, they would know logically what that traffic flow would look like as opposed to physical. All right? And that's kind of what the next section is about, interpreting a network diagram. And oftentimes you would perhaps implement different types of diagrams. You would have one diagram that would give you the physical topology, and you have another diagram that would give you the logical topology. All right, another consideration that you have to take into account when you're dealing with all these different devices and different components that run on the network is, what is the impact of the application going to have on the network itself? And this particular slide here really demonstrates kind of the difference between a lot of different applications in the network and how we need to consider the impact of those applications and their requirements on our network design and our implementation. Data typically is very forgiving, right? It runs over TCP, so there are mechanisms for identifying whether or not data is lost or data needs to be retransmitted in the form of sequencing and acknowledgments, so we can manage that. Most data applications are relatively capable of handling things like delays or dropped segments and so on. For example, if you don't get your email right away, is that really going to impact your overall production and whatnot if it's delayed by a couple of seconds and so on? So that's definitely something to consider. But the other nature of data is that data tends to be rather kind of mixed in its format and its size. So that's something that we have to consider as well. Some data applications require a lot of bandwidth. They can be very bursty. The datagrams themselves can be very large. So we have to consider what the impact is of having those large datagrams in our network is on maybe some of the other applications that are delay sensitive or drop sensitive or time sensitive. Voice is one of those types of applications. In this particular case, we're talking about real-time voice and communicating messages or communicating data in real time in the form of IP telephony or voice over IP. By its nature, voice data or voice encapsulated packets are relatively small, very benign. They range anywhere with overhead from 20 or 30 kilobytes per packet all the way up to 160 kilobytes per packet for like a G711 uncompressed codec. So that's not really, in the overall scheme of things, not really a very large amount of data that has to be processed. But voice, because it is real time, I'm having a real time conversation with somebody, I'm speaking with somebody on a regular basis, or having a two-way conversation with somebody, cannot be delayed or retransmitted because that would affect the overall conversation. So voice has, or real-time voice I should say, has some very specific requirements in how it gets handled on the network. 150 millisecond one-way delay, the latency less than 150 milliseconds, less than 1% packet loss. We can extrapolate those lost packets if it maintains a level below 1%. We don't have to retransmit those packets. We don't even have that capability really, because most real-time applications are going to be transported over UDP, the user datagram protocol, which doesn't provide for retransmissions, sequencing, acknowledgements, and so on. So less than 1% packet loss, we can kind of extrapolate those small pieces of information that get lost, and we can recreate those on the fly or simply ignore that loss and just move forward. And then bandwidth, again, relatively benign from a bandwidth perspective. The traffic flow itself is very predictable. The datagram sizes are very predictable because we're encapsulating specific time slots of information, 30 milliseconds or 20 millisecond time slots of information. One of the things that's missing from this particular slide, though, or this particular section, is jitter. Jitter is something that affects our voice quality quite significantly as well. Jitter is the variable delay between the transmission of those datagrams or between the packets themselves, the gaps between the packets. So if I'm interleaving large data packets and I'm processing large data packets through an interface, that could increase the gaps between those small datagrams, which then would result in a low mean opinion score, which is a way we measure the quality of voice, or some sort of it would have a negative effect on the quality of that audio stream. All right. Video pretty much has the same requirements, but the bandwidth requirements are much, much more significant because we're encapsulating a lot more information. Some of the video might be compressed and low image format, so it's not going to require a lot of bandwidth. Some of the other video might be full high definition video. Or we might have multiple streams that are being duplexed together, to provide some sort of teleconference solution or something like that. And then on top of that, we might be integrating other video services like streaming out some slide decks that we're trying to present or some other presentation and so on. So video has all of the same real-time requirements that our audio has, but in this particular case, the video is far more far less predictable with regard to the size of the actual streams. It can be consistent, right? We know that if I'm sending, video stream XYZ, I should see a pretty consistent stream of data with a relatively consistent size. But again, it's not kind of universally predictable, so we do have some additional requirements there. All right, and the same thing would apply with video with regard to jitter and so on. So when we talk about the different applications and how we classify them, are they interactive applications? Are they real-time applications that require fast processing and real-time processing? In other words, do we have to process those datagrams first? How much data is actually being generated? Is the data predictable? Is the amount of data or the size of the payloads or the packets themselves, is that predictable? These are things that we have to concern ourselves with. Is it drop sensitive? Is it critical to our business? Now, most of these things here that we see listed regarding interactivity, real-time responsiveness, the amount of data that's being generated, the burstiness, the drop sensitivity, these are all things that we can address with tools on the network to ensure that data gets treated differently. Those tools, we talked about that previously, are primarily related to implementing some sort of quality of service solution on the network. And that's what's going to provide us the ability to ensure that the data fits within certain criteria and the processing of that data fits within specific criteria. Whether or not the data is critical to the business, that's more of a concept that we identify from a business continuity perspective, from a business impact perspective, but certainly that's going to tie into the types of resources that we decide to allocate towards protecting that information, storing that information, making that information available to users, and so on. So definitely something to consider when we talk about just dealing with any kind of data in our network, is how critical is that data to our business. You see a couple of different classifications of applications here as well. Batch applications. These are applications that are typically used to replicate information or replicate data. So maybe Active Directory domain replication, or FTP data backups, or SCP data backups, you know, where we're taking information and we're copying it to a hot site or a warm site, or we're backing it up to some off-site storage facility, or whatever it might be. Batch applications are typically bandwidth heavy. They do require a lot of resources, but they're not necessarily time sensitive. And so we can run these batch applications at night when the network is not being utilized for other purposes or other resources. And we can make sure that these batch applications and the batch processes get scheduled at a time that it's not going to impact users. We can even create a secondary network. I've done this quite a few times for some of our customers. Create a secondary network that allows us to copy that information, you know, from one site to the other without using our primary in-band path, if you will. We have maybe a secondary route or a secondary path that allows us to copy that information. So that's a consideration as well. Interactive applications, these would be applications that are relatively robust applications. They're not necessarily drop sensitive or delay sensitive or time sensitive per se, but because they're interactive applications, meaning that the user is polling for information, or the user is trying to collect information from maybe a database or something, and the user is interacting with the application, time delays, and having to repeat tasks continually because tasks time out or they don't function correctly is something that's going to affect the user experience quite significantly. So we want to make sure that we treat these applications almost like real time, but it's more of a customer or user experience concern rather than the actual loss of information or loss of data. And then we have our real-time applications. These are the ones that we were talking about previously. Things like streaming audio or streaming video in real time through the use of telepresence, video conferencing systems, or IP telephony, telephony user endpoints, or devices like telephones in the network, and so on. All right, and again, that's probably going to be the one that's going to require the most attention from the perspective of usability. But again, those interactive applications do have some very specific requirements as well. I mean, how many times does a help desk you think here, yeah, it works, but it's really slow, right? I search the database, and it takes an hour for me to get information back from the database. I'm exaggerating, of course, but you get the idea. All right? So we have to kind of identify applications from that perspective as well. All right? All right. So that pretty much covers section number 1. We are going to get into section number 2 next. Section number 2 is the host-to-host communication model, where we basically will speak of different, the OSI model and the TCP/IP model. We'll talk about encapsulation and de-encapsulation and so on. So we'll see you guys in the next section right now.